Welcome to Physics Unwrapped YouTube channel. In today's video, I am going to solve KSET, that is Karnataka State Eligibility Test for Assistant Professorship previous year question papers on groups that comes under mathematical physics in physical science question paper. Yes, let us start with the first question. What does the question says? Relation between two finite groups in many to one mapping, then it is called. So it is a direct question. So according to the definition of automorphic relation and homomorphic relation, isomorphic relation and monomorphic relation, they have given the question. And this is a direct definition for homomorphic relation. What is homomorphic relation means? It is the relation between two finite groups in many to one mapping. Means we have a one group. A group contains A, B, C and D, and we have one more group called G prime that contains A and B, elements A and B. This is order of 4 and this is order of 2. Let us consider this is A prime and B prime. So here this element, many elements, it is mapping to one of the element of G prime, that is the definition. So this definition is the definition for homomorphic relation. So option B is the right option. What is this isomorphic relation means? One to one mapping. Okay, isomorphic relation is one to one mapping. Homomorphic relation is many to one mapping. Automorphic relation is one to one and onto mapping. And monomorphic relation is one to one, not necessarily onto. I hope everyone understood these definitions. So which option is the right option? Option B is the right option, that is homomorphic relation. Okay, yes, let us proceed to the next question. And this is also easy question. Under groups in KSET, they have asked very easy questions, that is like direct questions they have asked. G is a finite group of order n and A belongs to G. So they have given a group G. It is a finite group. They have said it is a finite group and it is of a order n. And this A, it is any element of this group G that belongs to G. Means A, this represents A belongs to G and order of A is M. Order of A is what? M. If G is cyclic, then M which is equal to N equal to 0, M which is equal to N, M greater than N, this can't be, and M less than N. Out of these three, any possibilities we have. Let us analyze this question. So G is a group, okay, and its order is n, okay, and A belongs to G. Any element in G contains the element A, and A order is what? A order is M, okay. So order of G is n, order of A is M. Now what they are saying, if G is cyclic, if we consider G to be cyclic, what does this cyclic means? What is the cyclic group means? It is nothing but the all abelian group is called as a cyclic group. Means all abelian group, what is this abelian group means? It should a group, if I say the set to be a group, if I consider this fourth I minus I, 1 and minus 1. This is, I am telling, a group of a fourth order. A group of a fourth order means number of elements represents inside the group to be a order, and I am telling it is a group of order 4. And if I want to say this is a group means it should follow some of the rules, right? It should follow the closure property and it should follow the associative property. It should follow identity element. It should contain the identity element as well as it should contain the inverse element under addition or under multiplication. If I said this is a group, okay, if I said this is a abelian group means under multiplication it should obey the commutative law, that is AB which is equal to BA, that is I into 1. If I consider any two elements, I into 1 which is equal to 1 into I, it should be 1 and the same. Then we call it as a abelian group. So this abelian group we call it as a cyclic group. All cyclic group is nothing but the abelian. I hope everyone is understood. Now, one more way of defining this cyclic group is nothing but a cyclic group can be generated from a single element. A cyclic group can be generated from a single element. For example, if I take this iota, this is an imaginary number, I to the power of 1 is nothing but I, right? Next, I to the power of 2 is nothing but minus 1. We have studied in the complex numbers. Next, I to the power of 3 is nothing but I square is minus 1 into I is nothing but minus I. Next, I to the power of 4 is minus 1 into minus 1, it will be plus 1. We are getting the all elements of the group from this iota, right? Instead of this iota, if you take minus iota also, you will get the elements. And now I call I to be a generator here. What I call I to be a generator means a cyclic group can be created from one of the element, and that element we call it as a generator. This is a one more definition of the cyclic group. Understood? Now, what is the question we have? G is a finite group of order n and A belongs to G and order of A is M. If G is cyclic, then orders they are saying M which is equal to N which is equal to 0. No, this is the wrong option. M which is equal to N and M less than N. This too is possible. When the order of a group and the order of an element same means if element is cyclic. If element is cyclic generator. Okay, if I call the element to be generator itself, then the order of the group and the order of the element is one and the same. If element is not a generator, they have not given here element to be a generator. Now the right option is M is less than N. I hope everyone understood this solution. Okay, let us proceed to the next question. What we have in the next question? The set of all non-singular square matrices of a same order with respect to matrix multiplication is a group. Just now I said the set of all non-singular means we are having a group of all non-singular square matrices of a same order with respect to the matrix multiplication. It is a group. Why it can't be a abelian group means they have given a non-singular square matrices of a same order with respect to matrix multiplication. It does not obey the commutative property, that is AB which is equal to element AB. This is separate element, this is separate element in the group. So if I multiply A into B under matrix multiplication, it won't be equal to B into A. So what is the commutative property? AB should be equal to BA. This property is not obeyed, then it is a group. If this property is obeyed, then we call it as a abelian group. Okay. Yes. Let us proceed to the next question. What we have in this question? All statement A, they have given all cyclic groups are abelian. And number 2 statement, they have given B statement, the order of a cyclic group is same as that of order of generator. Yes, in the previous question only it was very clear. I told all cyclic groups are abelian. Yes, from the definition, while solving the second question, I said, second slide, all cyclic groups are abelian. This is true. Means cyclic group obeys the properties of a abelian group. What are the properties of a abelian group? It should obey the closure property, associative property. It should have an identity element. It should have an inverse element. Then it should obey the commutative property under matrix multiplication, right? So all are obeyed here in the cyclic group. So we can say all cyclic groups are abelian. Now what is the statement B? The order of the cyclic group is same as that of order of a generator. In the previous question only I have told, if I consider the group, order of the group to be equal to M and the order of some element A to be equal to N, if these two is equal, they are saying yes, these two will be equal only from the definition. The order of the cyclic group is same as that of order of its generator. If I consider A is not just an element, it is also a generator like iota and minus iota. I said these two are the generators of some group I minus I1 and minus 1. So order of the cyclic group is same as that of order of the generator. So both the statements are true. So which is the right option? Option D is the right option. Option A and option B are true. Yes, let us proceed to the next question. What we have in this question, every isomorphic image of a cyclic group is cyclic and every homomorphic image of a cyclic group is cyclic. Now, in the first question only I said about isomorphic. Isomorphic is nothing but it is a group if we consider two groups, that is a set of two groups A, B, C and D, and one more group we have G prime to be A prime, B prime, C prime and D prime. There is a mapping of 1 to 1 mapping. Okay, 1 to 1 mapping of elements in the group, both the groups of order 4, then we call it as that group to be isomorphic group. And isomorphic image of a cyclic group is a cyclic. Yes, it is also a cyclic group. Next, every homomorphic, under isomorphic only we will get homomorphic. Homomorphic is many to one group, many to one mapping. Under a group we map many to one. So every homomorphic image of a cyclic group is a cyclic. Here also both the statements are true. So both A and B are true. So option A is the right option. Yes. Let us proceed to the next question. What we have? A one-to-one mapping of a finite group onto itself. Onto itself means it is a automorphism. We call from the definition a one-to-one mapping. Only one-to-one mapping means isomorphism. Many-to-one means homomorphism. One to one, not onto, not necessarily onto is monomorphism. What is automorphism? Means a one to one mapping of a finite group onto itself is nothing but a automorphism. So option C is the right option. Next, let us proceed to the next question. Quite a different question they are asking. The number of independent real parameter characterizing the group. It is a special unitary group of order 2. SU2 means, what does this SU2 represents? Means special unitary group. Special unitary group of order. This inside the bracket, if it is 2 means it is of order 2. Now what they are saying, the number of independent real parameters characterizing the group SU2. Means from the definition, what is a special unitary matrix? Means it is a matrix that comes under a unitary group. It's not a matrix, it is a special unitary groups. Means it comes under a unitary group and whose determinant which is equal to 1. Remember one thing, it is determinant which is equal to 1. Now we have a direct formula to find the number of independent real parameters characterizing the group SU2 is n square minus 1. This is the formula. So the number of independent real parameters can be found out using the formula n square minus 1. Here n represents what? Order. Now what we have a order? We have a order 2. Now substitute here. It will be 2 square minus 1. 2 square is 4 minus 1. The answer we are getting is 3. So which is the right option? Option C is the right option. Yes. Let us proceed to the next question. What we have in this question? Yes. Now the number of independent elements in a unitary group of order 2 cross 2 and determinant which is equal to plus 1. See, come back to this question. The same question they are asking again, but little modification is done in the question itself. The same question carries. Now, what we have in this question, the number of independent elements in a unitary group of order 2 cross 2. So, this is the definition of a unitary group. And they are saying, and determinant which is equal to plus 1. If you see, wherever the determinant which is equal to plus 1 means it is a special unitary matrix of order n. But here they have given to be 2 cross 2 means special unitary matrix of order 2. Previously only we have done this question. So the number of independent elements or the number of real parameters can be found out for the special unitary matrix of order 2 using the formula n square minus 1. So n square is nothing but here 2, 2 square minus 1, 2 square is nothing but 4 minus 1, that is equal to 3. So which is the right option? Option B is the right option here, right? Yes. Now let us proceed to the next question. What we have in this question? Yes, a one-to-one mapping of a finite group onto itself. This question again, it is a repetition question. They have repeated. That's what I am saying. Under groups, they have asked very easy questions, so it is easy to learn as well. So a one-to-one mapping of a finite group onto itself is, from the definition, it is automorphism. Okay. Yes. Next, we have a next question. The number of independent parameters of the group O3 and SU2 are respectively. We know that SU2 we have already done. Now let us study for the O2. O2 is nothing but the orthogonal group of order 3. For orthogonal group, O3 means it is a orthogonal group. Okay. Now for the orthogonal group, the formula to find the number of independent parameters of the group, that is O3, that is orthogonal group, is n into n minus 1 divided by 2. Here n is nothing but the order. Order what they have given? The order they have given it to be 3. So 3 into 3 minus 1 divided by 2. So it will be 3 into 3 minus 1 is nothing but 2 divided by 2. 2 get cancels. The answer is 3. Now what they have given, one more question in this question only, SU2, that is special unitary matrix of order 2. For this the formula we have already known. It is n square minus 1. Okay. Now n square is 2 square minus 1, it is 4 minus 1, that is equal to 3. So which is the right option? Option A is the right option, that is 3 and 3. Okay. Yes, let us proceed to the next question and the final question. Now, yes, what we have in this question, the group of order less than 4 is a group, they have seen it is a group which is having a order less than 4, then it is always cyclic, always non-cyclic, many or to many may or may not be cyclic under some conditions. So the option, right option is always cyclic. I have told you about the cyclic in the previous question itself. So under groups, I have solved 11 questions. All 11 questions were very easy to find out, and groups is a very easy topic to fetch the marks. Thank you for watching. For more videos under mathematical physics, you can visit my YouTube channel. I have uploaded many videos and I have solved many previous year questions on KCET, and it is also useful for upcoming assistant professor examination. Thank you for watching.